Okay, so I'm going to try to give an introduction to Teichmüller theory. It's a huge topic. So I probably won't be able to say much. I'm sure I'm not going to be able to say already all that I promised in the abstract. I hope I can say all that I prepare, but even that's not clear. What's most important is that it's clear. So just do interrupt me at any point if you have questions. And maybe just one thing, in case you're interested in this kind of stuff, there's lots of sources. One maybe good book, it's Farber Margolit's book. It's mostly on mapping class groups, but it has a good part on Teichmüller theory as well. A primer on mapping class group. And there's also a bunch of handbooks of Teichmüller theory. That's the title. I mean, it's a series. I don't know. I think we're at volume 8 or 9 or something. And it has many classical and less classical viewpoints on the theory. So if you're interested in more, that's definitely a good way to go. Okay, so what is Teichmüller theory? It's a study of a certain type of, for my viewpoint, it's a study of certain types of geometric structures, which are hyperbolic structures and surfaces. So for the mini course, I'm going to assume that I have a surface which is a closed surface of genus G, orientable. Whoops. Genus G needs to be usually at least 2. Sometimes we will look at the case of the torus. And I'm going to assume no boundary. Some of these things go through if some of these assumptions are not true, but not everything. I'll maybe try to say a little bit about what happens if you drop some of these assumptions here and there. But in general, this is really the setup. If I say surface, that's what I mean. And okay, let me start. So okay, one thing is there's many viewpoints to Teichmüller space. So I'm going to start the one that I'm most familiar with, which is the one of hyperbolic structures. So let me start with this. So what's a hyperbolic surface? Let me call it X. That's a topological surface. With a hyperbolic metric. So a hyperbolic metric you can divide into many ways. One way is you can say it's a Riemannian metric of constant curvature minus 1. It's a very quick definition. It's not really explicit in a way, in the sense that, well, unless you study this stuff very much, it might not tell you much. The way I like to think of it is that it's something that locally looks like the hyperbolic space. So it's something that's locally isometric to the hyperbolic space. So let me tell you what this is. There's various models. I'm going to take the model in which this is the upper half plane. So these are all the points in the complex plane with a strictly positive imaginary part. So this is the stuff here above. And there's two ways of, there's multiple ways of talking about the distance. One way is that I can say that the distance is obtained by integrating something that's a modified version of the Euclidean distance. So I divide by the imaginary part of z, which means that in particular, as I go close to the real axis, this distance explodes. So this is actually a complete space, meaning a line that goes to the real axis actually has infinite length. And one can also show that, for instance, there's an explicit formula for the distance. The distance between the points is the log of this thing here. I'm mentioning it because it might be useful for some of the exercises. Okay, there's a very explicit formula for the distance. That's something you can use. Something I would like you to understand about this is that it's a very concrete object. You might be very used to doing computations with the Euclidean plane with very little exercise. You can get very used to doing computations in the hyperbolic plane, and we know just as much, if not more. But so just to give you an idea, I imagine plenty of you know this stuff. If not, it's probably a very short introduction. We won't need that much about this. The geodesics in this plane are either half circles that are orthogonal to the boundary or vertical lines. These are the geodesics. So you see that you can, for instance, see that if you take a line and a point outside of it, there's infinitely many lines that pass through the other point, and they are disjoint from the previous one. So it's something a bit different than the Euclidean plane. And we can look at the directions at infinity, which is what is called the boundary of hyperbolic plane. So to go to the boundary, well, you can go to all of these points. So you can take a geodesic, you can follow a geodesic, you can go to one of the points on the real axis, but you could also go off to infinity that way. That's one single point. So this boundary is can be thought of as one. So yeah, you have a notion of boundary. And the last thing I wanted to say is that, okay, so a hyperbolic surface is something with a metric so that you're locally isometric to H2. Anytime you take a neighborhood, you can find an isometry with a neighborhood with an open set of H2. And another way of looking at those is as quotients of the hyperbolic plane. So if I have X a hyperbolic surface, and this is something we will use, then I can see this as the quotient of the hyperbolic plane via the action of some subgroup of isometries. And this is SL2R. And you need this group to be discrete as a subgroup of the isometry group, or of SL2R if you prefer. And you want this to be torsion-free. And well, in the case that we are looking at, you will also know more stuff about its elements. All of its elements except the identity are of a certain type. They are called hyperbolic, but I didn't want to go into detail about that. Okay, so these are the viewpoints on hyperbolic surfaces. I realize it's very short, but hopefully we won't need that much for understanding what's happening later on. So what we want to do is we want to understand all the hyperbolic surfaces of, say, the same genus or varying genus. So the obvious object we would like to consider, okay, we want to study hyperbolic metrics. So the classical object we could consider is we could look at all the hyperbolic surfaces which are of a certain topological type. So they are of homeomorphic to a closed genus G surface. For some fixed genus. And we usually just care about these things only up to isometry. Otherwise, you can create many, many copies of exactly the same surface. This is what is called moduli space. This is something that many people want to study. It's a already topologically complicated object. So one way of trying to study that is to say, well, I can try to look at its universal cover, look at its fundamental group, and try to understand this as the quotient of its universal cover via the action of its group. And what it turns out is that the universal cover of moduli space is Teichmüller space. This is topologically complicated. Not only topologically. So one strategy to study it is look at its universal cover and its fundamental group. And what it happens is that its universal cover is what is called Teichmüller space. And so this is actually the space we're gonna look at, which has many connections, and I mean it's interesting on its own. But to me, this is the way one way in which it naturally appears. So let me start by defining this from this perspective. So the Teichmüller space of surfaces of genus G, what is it? It's a space of pairs xf, where x is a hyperbolic surface, and f from the fixed genus G surface to x is a homeomorphism. And then I have an equivalence relation, where the equivalence relation is follows. So I have xf, this is the same as yh, if, so what do I have here? I have my surface S, let me drop the G. I have the map, one map to x. I have one map to y. These two are hyperbolic surfaces, so I can talk about isometries between them. And what I required is that there's an isometry between them, but something weaker. If I just ask for an isometry, we quotient down by isometry, we go back to moduli space. So I need a slightly weaker equivalent relation to get something that's a cover of this. So what we require is that the isometry is in a specific homotopy class. So what I require is that there exists, we call it y from x to y, phi from x to y, an isometry, which makes this diagram almost commute. It makes it commute up to homotopic. So such that H is homotopic to this, or said differently, phi is in the homotopy class of the obvious map from X to Y, which is F inverse composed with H. Okay, so it might look like a weird definition at the beginning. So let me just tell you one last thing. We think of this Teichmüller space as the moduli space, not of hyperbolic surfaces, but of what are called marked hyperbolic surfaces. And why do we say so? Because we have marked our surface with a homeomorphism from the specific surface S that we have and we fix and we never move to the X that we have. So this this map F here is what is called the marking. Okay, so once I have this map, I can tell you which part of the surface is which in an absolute term. Okay, let me give you a couple of examples. Yeah, there is a third one. Yeah, maybe that was a bit too. I know there's buttons, but. I will. But now everyone is awake. Okay, so maybe just a couple of remarks for trying to understand this equivalence relation, which is not obvious. It just takes a second to understand. If I have an isometry between two hyperbolic structures, two hyperbolic surfaces, then anytime I pick a marking, then by definition this will be in the same equivalence class as Y, where the marking is F post-composed with psi. Here, in this case, the diagram commutes with psi, commutes really on the nose, not up to homotopy. But we allow some wiggling. So the other thing is that if you look at something that's a homeomorphism of the surface, which is homotopic to the identity, then there's another way of constructing things that are in the same class, which is precomposing with this homeomorphism. And then maybe another example that might be a little confusing, but okay, I'm going to draw one hyperbolic surface. So I have my fixed S. I have a hyperbolic surface there, and then I kind of draw the same thing, but I reflect it. Okay, they are really supposed to be the same thing, but reflected. Then I have, so I can obviously identify this surface with this by saying, I bring this there and I move it. And I can do the same thing the other way. Okay, so that's something that is also maybe useful. So if I have a simple closed curve here, this map sends this curve to this one, and this one sends it to this one. And then same for the curve on the other side. I have a beta here. Via this map, it's sent to the big one. And via this map, it's sent to the small one. Okay, so for these two to be the same, what would you want? You would want that there's an isometry from this to this, which is in the homotopy class of moving this away and just squiggling it a little bit. Well, that is not going to be possible. I mean, you see, because essentially this curve here is very short. This is not going to be sent to something of the same length as the curve there. So what I'm trying to say here is that the pairs xf and the pairs yh are not going to be the same in Teichmüller space. So this is to say, I mean, that in moduli space, these two surfaces would be the same because they are isometric. But here they are not isometric through something homotopic to the identity. I need to completely reverse the thing to make them be the same. And that's not the map homotopic to the identity. So maybe that helps a little bit in understanding what this equivalence relation is. Any questions? I mean, probably the best way of understanding this is to sit down and try to understand a little bit what I wrote so far meant, but just to ask me at any point if something is unclear. And I wanted to quickly mention one specific case, kind of the baby case that's a torus. Okay, so here we are already going to have to change some things because there's no hyperbolic structure on the torus. This is Gauss-Bonnet result. It tells me that if I have M, which is a closed surface with a Riemannian metric of constant, I'm going to say, well, not necessarily constant, with Riemannian metric of curvature K, then what I have is that there's a relation between the topology and the geometry. So 2 pi times the Euler characteristic of the surface is the same as the integral over the surface with respect to the area of the curvature. So if K is constant, the second part is just the area times K. And then this part is okay, so that means if I have the torus, the Euler characteristic is 0. So if M is the torus, then the Euler characteristic of the torus is 0. So the only way that I can have this to be equal to K times the area is that I have k to be constant equal to 0, k to be equals to 0. So what I'm saying with this is that if I want to look at constant curvature metrics on the torus, I'm not going to find hyperbolic ones for which the curvature is -1. So if I want to define a Teichmüller space for tori, I'm going to have to change something there, and I'm going to choose the appropriate type of constant curvature metrics. I'm going to choose flat metrics instead of hyperbolic metrics. And there's another fact, another remark, is that if S is a surface of genus G, and K is constant equal to -1, what do we get from that? We get the 2 pi, the Euler characteristic is equal to minus the area of the surface. This is the hyperbolic area. This in particular tells me that if I fix the genus, the area is constant. The area doesn't change. Instead, if I fix the genus, if I fix genus equal 1, I have no constraint on the area. It's 0 times the area is equal to 0. The area can be anything. So there's kind of an extra parameter in the case of the torus, which is this rescaling that does not exist in case of hyperbolic surfaces. So to actually have an analog of Teichmüller space, I'm also going to fix a normalization on the area on the surface of the surface. Okay, so for the torus, I'm going to say that Teichmüller space, this is the analysis of that one in this setup. It's the set of, again, pairs, where X is a flat torus, so a torus with a constant 0 curvature Riemannian metric of area 1. And then F from my fixed torus to X is a homeomorphism. And then the equivalence relation is the same. So here again, I have X F, which is the same as YH if there exists phi from X to Y, an isometry. Now it's an isometry of flat tori such that let's say phi is homotopic to F inverse composed with H. And what I want to sketch here is the fact that in this case we can really compute Teichmüller space, and it is actually going to be the hyperbolic space, hyperbolic plane. I don't know if theorem is really a word, but it's really the right word for this, but okay, I mean, for what I'm going to say at the moment, it's really just an identification. It's really just more a bijection, and then there's way of making this into much more than a bijection. But I have designed at the moment Teichmüller space really just as a set. So this is the only thing we can talk about. And the idea of the proof is it goes in 2 steps. So the first one is that we want to identify Teichmüller space with lattices, with a certain space of lattices in R2. So these are what are called marked lattices in R2 modulo an equivalence relation. So here equivalence relation is going to be isometries and homomorphies of R2. And here a marked lattice is a lattice with a fixed set of generators, ordered set of generators. marked is a lattice plus an ordered set of generators. So a lattice is just, in R2, it's just, one way of looking at it is I take two linearly independent vectors and I take the z linear combinations with integral coefficients. There's a much more general definitions. We will hear much more about it later on, but you can think about it that way. So here I have a lattice lambda, and then I have generators, say u and v. So I have that lambda is u, z. It's something of the form. Do I want to put them later? I guess I want to put them later. Okay. And the idea for this identification is that if I start with something where X is a flat torus and F is a homeo, okay, so I have my fixed torus T2, and I can fix a generating set of its fundamental group. How do you have I called them? So the fundamental group of T2 is generated by these two elements that commute. And so if I have a map from here to there, I get a map at the fundamental group level. Let me call it, I don't know, F star from T1 of T2 to the fundamental group of X. And so in particular, I have these two elements and I can send them there. These are going to be generators of the fundamental group of the flat torus. And the other thing we need to know is that the universal cover of the torus can be identified with R2. I mean, this is really isometrically, so if I also lift the metric from X to the universal cover, I get a flat metric. So this is topologically, but also geometrically R2. Okay, so let me call this U and V. And so what we have, so then the surface X is the quotient of its universal cover by the action of the fundamental group. This is R2 modulo the action of lambda, where lambda is the one generated by these two, generated by, what am I going to say? U and V. So this gives us a way of associating two, a pair, X, torus, and homeomorphism, a lattice with two generators, and you can go backwards. I mean, if you have a lattice with two generators, you just take the quotient, and you go backward. The only thing essentially you need to show is that you can reconstruct from the fact that you know where the two generators A and B go, you can reconstruct a homeomorphism here. And I'm just going to assume it. Okay, this is one way. This is one thing, and then the other thing is now I wanna give a space, a parameter space for these marked lattices. Modulo the same equivalence relation. Now I want to put this in correspondence with hyperbolic space, and what do I do is that if I take lambda with two generators u and v, now what I can do, so I can move this in its class by isometries and homotheties. So what can I do? I can first of all rotate so rotate and rescale this lambda and so its basis, so that u is sent to 1. Now v is sent to, so u is equal to 1, or is sent to u prime equal to 1. Now v is something that is linearly independent with respect to 1, so it's not real. So it has imaginary part that's different from 0, and up to symmetry, you can also assume that its imaginary part is positive. So if needed, so that v is actually a tau where the imaginary part of tau is bigger than 0. And so now you have an obvious way of identifying this to this tau. So this means that tau is in H2. So it's easy to go the other way. I take a tau which is in H2, and I take the lattice that's spanned by 1 and tau, and I take the torus that's associated to that. I make the lattice that's associated to that with this generating set. And all that needs to be done is to show that these are really actual bijections. I mean, there's lots of equivalence relations that are going around here. So you can try to look at the details if something is missing, if something confuses you. Okay, so the torus is this nice simple case in which we understand completely the structure, and we will use it also later on, but it's a case in which everything is easier. In general, we don't have such a good description such an explicit description for Teichmüller space, even though it's actually not that bad. Okay, let me see. Let me try this. For the people based in Germany in the audience, do tell me what I'm doing wrong. And I know I am supposed to be able to do it at the same time with the two, but it's like trying to do computations on the board. It's not a good idea. Okay. Now, so something I would like to tell you is one reason why we might like Teichmüller space, despite the fact of it that its definition is weird, is because we can call geodesics and curves by their name. So to tell you that, I need to first tell you something about hyperbolic surfaces, which is that if I have X, a hyperbolic surface, and I have alpha, which is an essential closed curve, And in our case, essential just means homotopically non-trivial. So non-contractible. But sometimes you want surfaces to have punctures, and in that case, you actually don't want it to be homotopic into a puncture. So the general definition is that it's cannot be homotoped into a disk with at most one puncture. So this is so for instance, it cannot be a circle that surrounds a single puncture. Then there's a nice fact that actually works more generally. It's a negative curvature fact, is that in the homotopy class of this curve, there is a unique geodesic representative. Closed geodesic. In the homotopy class of alpha. And also, one can find this one by looking at the closed curve in the homotopy classes as the shortest length. In this same homotopy class. So the picture is a bit the fact. It's the reason why I want to draw really hyperbolic surfaces a bit like this, is that if I start with some curve, then this really, this cylinder shrinks down to something in the middle. There's a unique shortest curve, which is there in the middle, which is this thing here. This is in the case of simple curves, but the result is true more generally. And yeah, so there's this nice fact that if alpha is simple, then alpha sharp is simple. So maybe the moral of the story is that in hyperbolic surfaces, when we have curves, the simplest representatives of curves are usually the ones that are geodesic with respect to some hyperbolic structure. So sometimes also when we just want to do things about topology, it's useful to fix a hyperbolic structure to find good representatives of our curves. Okay, and then, so the consequence of this remark is that we can define the length of a homotopy class of a curve. So if A is the homotopy class of an essential curve, on a hyperbolic surface X, so we can define what I'm going to call L subscript A of X, which is the length on X of this, the unique geodesic representative Okay, and I'm just going to introduce a little bit of notation. I can look at the homotopy classes of essential closed curves. I call this C star of S. I don't know how to call it. So this is on a, now it's a topological thing, so you can assume that S is just a topological, yeah. Oh, sorry, no self-intersections. So this is simple, this is not simple. I mean, what I'm saying here is that, like, if you look at the simple case, in the homotopy class of a simple curve, you can also have non-simple curves. So geodesic representatives, they minimize something geometric, the length, but they are also good topologically. They minimize the number of self-intersections. Okay, so homotopy classes of essential closed curves. And I can look inside at the ones that are simple. And here I mean that the homotopy class is simple if there is a simple representative. And something that's nice about Teichmüller space is that I can define a length map. So anytime that I take an essential, a class in here, I can define this function, which is why I wanted the A to be lower from Teichmüller space to R, the positive ones. How do I do that? I pick the class of X F, just for simplicity, let's say this is the class of some curve alpha. Then I can look at the length of, now I need a curve on X. There's an obvious way of getting a curve on X starting from a curve on S, which is F of alpha. So I take the class of F of alpha, and I look at its length on X. Okay, and I cannot do this on moduli space because I don't have an identification between S and X. It's kind of that drawing there. I don't know whether in moduli space, I don't know whether the red curve, I don't have a way of identifying the red curve with the red curve above. So that's kind of one advantage of Teichmüller space. And okay, so here again, there's a bunch of things to check. There's a bunch of up to homotopy that are floating around, and what one needs to do is to check that everything works well. If you are uncertain about the definition, it's an excellent exercise to figure out why this actually works. But I mean, we'll need this later on. It's not only that I'll do it a bit later on, but the fact that we can do something like that will allow us to give global coordinates for Teichmüller space, which is not something that we can do on moduli space. Maybe something I can add is that there's many good sources for these kind of results really on hyperbolic surfaces. I think my favorite is Buzzer's book, Geometry and Spectra of Compact Riemann Surfaces, where all of these things are described. There's an introduction to hyperbolic space. There's the formulas that we talked about before. So if you want more details, that's also a good source. Okay, any questions before? So far we were in supposedly viewpoint 1, that was a hyperbolic matrix, and I want to go to the second viewpoint, which is Riemann surfaces. So something that's very nice about this area is that this space can be interpreted in many ways. And so this is interesting for many people from different viewpoints. And now this is something that could be either taken as a definition if you had not seen the one before, or if you like this more, or as a fact that these two things are the same, as a theorem, that this is the same as, it starts very similar, but now, so F is still a homeomorphism from your fixed surface, but X is not a hyperbolic surface anymore, it's a Riemann surface. So it has a complex structure, and then we have a similar relation. Now the thing is very similar to before, except that we don't talk about isometries anymore, but we talk about the good maps in the realm of Riemann surfaces, which are biologomorphisms. So where, if I have two pairs, they are equivalent if there exists theta from X to Y a biholomorphism. Such that, and then again we have the same diagram as before, and I want that this almost commutes, so commutes up to homotopy. And I want to give you an idea of why this is the same as the previous space. And for this, we need the uniformization theorem. Which tells me that if I have a simply connected Riemann surface, then I have very few possibilities. This is biholomorphic to one of three cases. And it's exactly one of those. So it's either the hyperbolic plane, seen as just at the moment really just as a subset of C, C itself, or the Riemann sphere. So C union a point at infinity. And so the corollary of this is that if I take a Riemann surface, if I look at its universal cover, by definition the universal cover is going to be simply connected, and it's going to be a Riemann surface with the induced hyperbolic structure. Then its universal cover is either, the hyperbolic plane, C or C hat. And then another, okay, so, and in particular, this means that then X can be seen as the quotient of this modulo some group. And this group now is going to be a discrete group of biolomorphism. That preserve X tilde. And now the fact that we need is that if the genus is at least 2, this universal cover is actually going to be the hyperbolic plane, and the biolomorphisms preserve the hyperbolic metric. Okay, so now this gives us a way of starting with a Riemann surface and constructing a hyperbolic surface via this uniformization theorem. Okay, you look at the universal cover, you identified with H2, and you look at the gamma that you get, and now the quotient of H2 mod gamma is going to be a hyperbolic surface, and you need to transport the marking from one place to the other. But this hopefully gives you a bit of an idea of why these two definitions are the same. I mean, there's clearly details missing. But okay, so this is a bit quick. But I wanted to introduce a third viewpoint as well, which is that of representations, which is certainly dear to many people in the room. Okay, so the third viewpoint it's something that starts with more algebra. So Teichmüller space can be identified with the space of representations, so homomorphism, from the fundamental group of your surface into PSL2R. And I just want good representations. I want them to be discrete and faithful. And here, so rho is discrete if, let me say, if the image is a discrete subgroup here. And it's faithful if it's injective. It's just a fancy way of saying injective. And we need an equivalence relation, which is conjugation by PSL2R. So here, so PSL2R acts by conjugation. So if I take a matrix in PSL2R, and I take a representation here. I get a new representation by conjugating the image of every element via A. So this, where gamma is in pi1 of SG, is A rho gamma A inverse. I might have switched the A with the A inverse. If so, someone should complain. So yeah, this is the actual by conjugation. Okay, and again, I want to give you an idea of why this is the same as hyperbolic metrics or Riemannian, so marked hyperbolic structures or marked Riemannian Riemann structures. And I'll give you a quick idea, and one exercise is to fill in the details. And so the idea of why we have this identification is that if I take a pair where this is a hyperbolic surface, then its universal cover can be identified isometrically with the hyperbolic space. This is the thing that I had mentioned at some point by saying that every hyperbolic surface can be realized as a quotient of H2. So there's some identification there, and this is an isometry. And then I have a map at the fundamental group level between the fundamental group of SG and the fundamental group of the surface, which is induced by the marking. Now this one acts on X tilde by isometries. So what I actually get through this identification, I get an action of this one on H2 by isometries, which means that I can actually, so this is going to be without fixed points, and it's going to be a discrete action. And so this means that I can actually identify this one with a group of isometries. I had not put the P before, but I hope you'll forgive me. So I can identify this. I can see this is a group of isometries of H2, so I can identify it with the subgroup here. And that's the way of how you start with a hyperbolic surface and you construct a representation. And vice versa, if you start with a representation, then you get a subgroup, a nice subgroup of PSL2R. You just take the quotient of H2 by this subgroup, and this gives me a hyperbolic surface. And then you need to think about the fact that you also get the marking. And maybe this is a good point to say something about non-closed surfaces. Here, things get significantly more complicated when the surface already has boundary or cusps, because there's multiple surfaces that have the same fundamental group. So in the case of closed surface of genus G, two different surfaces have different fundamental groups. So here, this I can think of it as an abstract group, and it's all perfectly fine. If I look at all the discrete and faithful representation, they give me a hyperbolic structure on the same surface. But if the surface is not closed, then different surfaces can have the same pi1. same fundamental group. And so somehow we will need to be careful, and we cannot choose all of the discrete and faithful representation. There will be more conditions to tell me that I am actually choosing something on the correct surface. I mean, I don't have the time to go into this. I just wanted to point out that this is actually something where we need to be careful. And I want to say that if, so in general, if your surface is a closed surface and you remove finitely many points, this is still not that bad. There's finitely many surfaces that have the same fundamental group. But if you are like me and you don't mind allowing surfaces which are called of infinite type, so if S is of infinite type, which means that the fundamental group is not finitely generated, and in practice this means that the surface could have infinite genus, could have infinitely many punctures. So examples of these are, you can imagine to have a surface like this, or you can have the plane with lots of points removed, and there's many more. Then every such surface has the same fundamental group. It's always the free group on countably many generators. So if you look at that, if you just look at this definition, you won't get something that's associated to your specific surface. And so you'll need to be much more careful. Okay. Okay, one word on another viewpoint that I'm really just going to mention because it might be interesting for someone is conformal structures. Then I'm going to go back to something where I'm a bit more precise. So what I'm just going to say is that we can identify Teichmüller space also with space of marked conformal structures, which are defined. By now we know how this starts. So here I have X. Now it's going to be an Riemannian metric. And I have my homeomorphism. And now the equivalence relation is going to be much bigger. I'm going to identify very many things. So I identify two classes, two pairs, if there exists a conformal map, or let me say, if this is homotopic to a conformal map. Right, there exists a conformal map in this class. I'm writing the same equivalence relation in many ways. These are just maps that preserves the notion of angles, and in practice what one can show is that in such a conformal class there's a unique hyperbolic structure, which is why this goes back to being exactly the same as Teichmüller space as I defined it in the first viewpoint. Okay. So what I want to talk about now is how to give coordinates to Teichmüller space, and this is where these length functions are going to be useful. Okay, and to do that, we need to talk about Pans decompositions. So to define coordinates, we need to fix something. So I fix P, which is a Pans decomposition of my surface. What is a Pans decomposition? This is a maximal collection of essential simple closed curves on the surface. There's many ways of defining it. On S, which are pairwise disjoint and pairwise non-homotopic. And another way of saying it, here there's something to say, is that this is the same as a collection of such curves that cut the surface in what we call pairs of Pans, which is where the names comes from. So this is a collection of essential simple closed curves on S, pairwise disjoint, which cut the surface into three-hole spheres, or punctured spheres, depending on how you prefer to think about it. And these three-hole spheres are what we call pairs of Pans. And the fact is that we know how many curves we have, and we know how many pairs of Pans we have. That depends on the topology. There's 3G minus 3 curves, and there's 2G minus 2 pairs of Pans. So there's many Pans decompositions, but we fix one. I'm going to draw one in a second. So this has 3G minus 3 curves, and it cuts into 2G minus 2 pairs of Pans. So what the equivalence that I haven't shown of the two definition tells me is that I can just start drawing things that are disjoint, and then at some point I'll have to stop, and that will give me, now I'm making it unnecessarily complicated for myself. Maybe something like that. This should be correct. This is a Pans decomposition, and if I cut along those, for some it's easier to see, for some it's less easy to see, but you can check that they are all spheres with 3 holes. So once I have that, so I fix this collection, for each of these curves, or for each homotopy class of this curve, I can look at the associated function on Teichmüller space. So I get 3g minus 3 length functions on Teichmüller space. So I fix it, let me call it P alpha 1 to alpha g. Oops. To alpha 3g minus 1 minus 3. Let me say AI is the homotopy class of alpha I, and then I get 3g minus 3 length functions LAI from Teichmüller space into the positive reals. And we call these the length coordinates. They are not enough to define a point in Teichmüller space, but they are not super far from being enough. So now actually the Panzer composition is not enough to define the coordinates. We need an extra set of curves. So we also fix Q, which is a collection of, again, essential simple closed curves on the surface that have good intersection properties with the ones that I have. So such that every time that I look at Q and intersect it with a pair of pans that I obtain by cutting along P, then this collection is exactly 3 arcs, each connecting 2 different boundary components. Okay, so let me maybe draw one such curve, or maybe 2 such curves. Here, so this in green is P, and then I can, this is a curve in Q, and I can also choose, for instance, this as a curve in Q. So now if I look in this pair of pans, when I cut along the green lines, I have this arc, and this arc. These are 3 arcs that join the 3 boundary components of these pair of pans. Okay, and now I need to say, so I fix one of the curves in my pan's decomposition. Now I can look around it. There's 2 possibilities. Say if the curve is this one, there's a single pair of pans that's attached to it. This happens when the pair of pans is glued together with itself along this curve. And if I look at this one, there's 2 pairs of pans that grow out of that. So I'm in one of 2 situations. So either I have locally the situation, I can look at it this way. I have alpha I, and then I can have 2 pairs of pans. Maybe some of these are glued to each other. Or I have, whoops, not this one. Or I have this one. And And now what can I do? I can, so let me do it. Like I look at this curve here, eta, and suppose that my alpha I is that one. Then for the second case, it's analogous. So alpha I could be this one. Okay, so now here I'm on X. So these are not alpha I, but it's f of alpha I. So I'm fixing a point in Teichmüller space, and I want to define some other number associated to this alpha I, which is going to be the twist, which informally tells me if I have these two pairs of hands, which have the same length of a boundary component, which tells me how I glue them. So there's these two circles, I need to glue them by an isometry. There's not a unique isometry. And so I need to tell you which one I'm choosing. And so what happens is the following. First of all, you can always pick two orthogonal arcs. So now this is a hyperbolic surface. There exist hyperbolic arcs, and they are unique, joining two different boundary components or the same boundary component to itself. So these are beta 1 and beta 2, and otherwise here it might be this. Beta, and this is a geodesic orthogonal to the boundary components of the pairs of hands. Sorry, what I'm not saying here is all the time I always want to pick the geodesic representatives of everything. And now I look at the image of eta via the map F. It could do something. It could, for instance, do this. So it might enter, and then maybe it will turn around here a bunch of times. Whoops, not ideal. Sorry. This is a piece of f of eta. And now I want to look how many times essentially this winds around. Okay, so what I'm saying here is that if I look at this relative to the boundary here, f of eta, so if I fix this bit between the two boundary components, how can I describe this? I can follow beta 1, then I need to do a bunch of tours around the green one, and then I need to do beta 2. So this is going to be homotopic to beta 1, then a certain amount of times that I do the thing in the middle, and then beta 2, well, inverse if they, well, depending on the order that you chose. So there's some number k that comes here, and k is an n in Z. This is up to homotopy. And so I can define the twist. At alpha I of my surface. This is this is k times the length of alpha I on my surface, and then plus or minus, depending if I need to go to the right or to the left, the distance between P1 and P2, so plus is if I need to go to the left. Now I'm going to tell you what, and minus is if you go to the right. And P1 and P2 are these 2 points here where the two beta 1 and beta 2 project onto the curve. Okay, so what does that mean? There's one part that tells me, okay, I want to know what's the distance between these two. And then there's one part that tells me how many times I need to go around my curve, how many times I need to twist one pair of pants before gluing into the other one. It's quite annoying written like this, and usually people don't do it. But, but otherwise, it's, yeah. So the intuition is really what I was telling you, but if you want to do actually something concrete, I think you need that. And so apologies for this technical bit. I'm just going to write the theorem on the coordinates, and then I'm going to stop. The point is that these numbers that we define are enough to determine the point in Teichmüller space, and these set of numbers actually really give you a set of global coordinates, and they are called Fenchel-Nielsen coordinates. So I need to know the lengths of the pairs of the boundary curves of the pairs of fans and how to glue them. Okay, so the theorem is that if I have P and Q as before, then the function, let me call it Fn, actually it really depends on P, from Teichmüller space to what do I have? I have the length, those are positive, and the twists could be positive or negative, those are the twists. And I have 3g minus 3 of each of these, so I take xf, and I send this to the length. Sorry, I'm gonna forget the sum brackets for because they become too many. This thing is a bijection. And these ones are the twist parameters. Okay, and if you have missed a bit how to construct the twist parameters, it's not that bad. You just need to know that there's global coordinates, and they are very nice, and we can really identify Teichmüller space with r to the 6th, well, with a subset of r to the 6g minus 3, which is a pretty easy subspace. I'm gonna stop here and talk about it more in the next time.
Let's thank the Any questions?
Not to be annoying, but in viewpoints 2 and 3, do you not get 2 copies of Teichmüller space via this?
Yes, probably, yes. Okay, yeah, here, yes.
And up there, maybe you want F to be orientation preserving or something?
Yeah. 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 Let me think if I don't always get 2 copies. It might be that as I've defined it, I always get 2 copies.
No, I think in the first definition you don't, because psi or whatever you called it didn't have to be orientation preserving, whereas here a biholomorphism has to be orientation preserving.
Fair point.
Yeah, and there I think it's fine. But anyway, sorry.
No, that's a good point. I mean, it might be clear from from everything that the hyperbolic viewpoint is my favorite. So I will certainly make more of these mistakes later on. Yeah.
Sorry. So these the Fenchel-Nielsen, do they only depend on P or also on Q?
I only on. Yeah, I think you need Q as well. Certainly you needed to define them. And then I was not entirely sure, and I haven't thought about it long enough, whether if you take a different Q, you get the same. No, but I think you really need both. At least for defining them, you certainly need both. And I need to think about it for a second longer.
Are there any other questions? I have a slightly annoying question which I missed taking notes. So the plus, where you say the plus in the definition of the twist, is if you go to the left, if what goes to the left?
Okay, depending on whether the 2 yellow arcs could be in 2 different positions. So when you follow your curve eta to you'll do full tours around alpha i's, and then at some point you need to, so you arrive with beta 1, you need to do a full tour, and then you need to either go to the left to join beta 2 or go to the right to join beta 2. Because the full tour, so you, okay, let me say it here. Okay, I want to write this as this concatenation, so what do I do? Relative to the boundary, I go here, then maybe I need to do, now I think here I want to go to the left, I do, I don't know, 3 tours, I arrive here, and then I need to either go to the left to join beta 2, or beta 2 could project here, and then I need to go to the right.
Thank you. If there are no further questions, we thank Federica again.